So next to the Pythagorean theorem, this is one of the most powerful, or identity, excuse me. This is one of the most powerful identities. So we're going to look at the cosine difference of angles. And to do that, we're going to do a little bit of review of the unit circle and the distance formula. So what I want to do is I want to try and come up for a formula for the cosine of the difference of two angles. And to do that, I need to look at an angle alpha and beta. So I'm going to hang out quadrants 1 and 2 here. And I'm going to say blue that this angle here is going to be my beta. And then this angle over here is going to be my alpha. So then this angle in between here would be alpha minus beta. And I can take that angle and I can slide those two down so that around here-ish is going to be another point, so that the angle measured in standard position is also alpha minus beta. And then I just want to note, there's 3 points I've just created here, at least. I've got these blue points here. The first one is cosine of beta for x and sine beta for y. Second point, cosine alpha, sine alpha. And then that red point I created has an x value of cosine of alpha minus beta and a y value of the sine of alpha minus beta. And what I'm going to do next is just make a note that because of the rotation I did here, the distance, the chord between these 2 points has the same length as the chord between these 2 points here. Not quite to scale, but let's make believe. So those 2 chords are the same. How do I find the length of the chords? Well, I'm just going to use the distance formula. So distance formula says take your y's and subtract them and square them, and take your x's and subtract them and square them, and then take the square root of that sum. So we're going to do that for the blue points and then the red. And the red is also connected to the point over here, x is 1, y is 0. Well, for the difference in the y values for the blue points, the y values are just the sines. So I'm just going to take the sine of, say I want to write in red here, blue, sine beta, sine alpha, sorry, minus sine beta. That's the difference between the y values, and then I have to square that. Same for the x values. So that would be cosine alpha. And it's cosine beta squared square root. So given an alpha and a beta, I can calculate the length of that first chord. Now with the red points, the y values are first sine of alpha minus beta minus y value of 0. And then our x values, cosine alpha minus beta minus 1. And distance formula says take the square root of that sum. And I designed this relationship so those two distances have to be the same. One set of points is just a rotation of the other set. So comparing these two, since they both have a square root, I could square both sides and get rid of it. I don't really need the square roots anymore. Then I'm left with all that squared stuff. Well, I'm going to have to square some of that out. So give this a shot. What's it going to look like when you take sine of alpha minus sine of beta and you multiply it by itself? Write down what you think that's going to look like.
Wait, what?
We are going to need to square this difference. That means we have to multiply this by itself. What are you going to get when you multiply that by itself?
When you just boil it?
Yes,
Okay.
do it.
Okay.
You get it started, then I'll catch up. You'd get something like that. You should find you have a sine of alpha squared, you have a sine of beta squared, and then you get to multiply the sine of alpha times the sine of beta twice. And they're both subtracted, so we're going to have a -2 sine of alpha sine of beta. We're going to do the same thing for the cosine alpha minus cosine beta, which is going to be just like this, but with cosines. And so I think we could just write down that next. So then I'm going to have a plus cosine squared alpha -2 cosine alpha cosine beta plus cosine squared beta. And before I move on to the red stuff, there's some really nice things hiding in here. Whenever I see cosine squareds and sine squareds, I'm thinking, ooh, if I can add those together, they add up to 1. Do we have any lucky winners here? Let's see, I've got a sine squared alpha plus cosine squared of alpha. Those cancel out to be 1. That's nice. So I'm just going to make a note here. Those guys can go, and I can replace them with a 1. Anything else nice like that?
Sine squared of beta.
I've got a sine squared of beta plus a cosine squared of beta. So those guys are going to give us a 1 also. That's nice. Thank you so much. So I get to add in another 1. Otherwise, I'm going to get those two unlike terms. So I have a -2 sine alpha sine beta. And I have a -2 cosine alpha cosine beta. Let's look at the red part next. So again, since both the blue and the red have a square root, I can make the square roots go away by squaring both sides. So I have to square the sine minus 0. Well, the sine minus 0 is just the sine, so I just have a sine squared. That's nice, okay. So we're going to get a sine squared of alpha minus beta. What else do we get? Here, I'm going to have to multiply this one by itself. So that's going to end up being cosine alpha minus beta minus 1 times cosine alpha minus beta minus 1. So FOIL that out, see what you get. Not that bad. Let's see, so I'm going to get cosine squared. -1 times -1, that's nice. And then otherwise, I get a negative cosine alpha minus beta minus another cosine. So there's minus 2 of them. And then a plus 1. A little better than the blue one. The blue one was a lot more work. Anything magical happen here?
The first squared.
Yeah, sine squared of an angle, cosine squared of the same angle. Doesn't matter what the angle is as long as it's the same angle. That's another 1. Goodbye. I love that identity. So we're going to get a 1 instead of those. There's another 1 over there. Okay. So what's left? Well, the green and the red are actually equal. So I'm just going to write this red next to it. I'm going to get a 1 plus 1, which is a 2. And the only other thing left is the minus 2 cosine of alpha minus beta. Over here, I've got the 1 plus 1, which is also a 2. Everything has a 2 in it. We could divide everything by 2. All right, let's do that. Oh, wait. And then there's a plus 2 on each side. Can I subtract that away? There's lots of interesting things here. So just note, I have a plus 2 over here. I have a plus 2 over here. Those are going to subtract off. Otherwise, I can divide everything by -2. Right? -2 times, -2 times, -2 times. All right, here's what I think is left. Sucker up a little. On the left side, after I subtract 2 and divide by -2, I'm going to have a sine of alpha, sine of beta. I divided by -2, so I'm going to have a plus cosine alpha, cosine beta. These 2's get subtracted away, divided by that -2, so this is now equal to the cosine of alpha minus beta. And that crazy geometry gives us a very powerful formula here for playing around with sines and cosines. And this leads to about 20 other important formulas. Now, I don't expect you to prove this on your own. My point is everything in trig has a reason. There's interesting relationships between sine and cosine. They're like endless relationships. Some of them are very important, like the Pythagorean identity is a very important one. This angle difference is very important. The angle difference is going to lead to an angle sum formula, and the sum to product, and product to sum, and a ton of other ones. So over the next week or so, we're going to explore all the variations of this. Along with knowing the Pythagorean identity, I recommend this one is also one that you commit to memory. So I'm going to give you its other variations. So I've got angle, sum, and difference formulas. All right, so the first one I just did was the sine of alpha, oops, that minus beta is equal to, no, not the sine, the cosine. We'll get to the sine in a minute. Cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. If we replace the difference with a sum, it's a really easy switch in the formula. It's going to lead to cosine alpha cosine beta minus sine alpha sine beta.
I need to talk to whoever came up with these.
But we're going to play around with them for a while. So all that is a replacing beta with negative beta, which just leads to a little sign change there. Now remember, the sine and the cosine are just a shift of each other. Right? We can shift by pi over 2, either one to get the other. So if we apply a shift like that, then we can turn these into sine formulas. I'm not going to go over all the details. I'm just going to give you the end result. After such a shift by pi over 2 of this angle right here, we get a sine difference formula that ends up being the sine of alpha cosine of beta. There's the shift, we switch a sine with a cosine, plus the cosine of alpha sine, minus, sorry, sine of beta. If we switch the difference to a sum, we get sine alpha plus beta. It's the sine of alpha, cosine beta, and we just get a plus in the middle. Cosine alpha, sine beta. So some things that help me remember these is the sign gets the signs right. Notice the negative on the left and the negative on the right. Cosine really loves itself, so it starts off with a cosine cosine. Because I used the cosine to get to the sine, I had to do a little shift, trading a sine for a cosine. So then we have to start flip-flopping with the sine. Sine alpha cosine beta, then cosine alpha sine beta. In my opinion, the most important one here is the one I started with here, because that one leads to a ton of other formulas. Here I have 3 more. There's, I guess, 20 something. There could be more that all generate from this. All right, so let's apply these. So I can use these formulas to do things like calculate the cosine. Now, warning, I rarely play with degrees, but I'm going to a little bit today. Radians are better. So I get 75 degrees. That is not a special angle. But it's related to some special angles. Anyone see how 75 is related to some special angles we know? Which ones?
60.
60 and 15 is not special.
30 and 45.
45 and 30. Yeah, so I could say, well, that right there could be written as the cosine of 45 degrees and 30 degrees, which means I can use this formula up here to split it up.
Oh, yeah, this makes sense.
And I can come up with an exact answer for a lot of other angles based on the special angles. But it turns out the special angles are a little bit more powerful than we initially thought. So according to my formula, I'm going to get that this is equal to the cosine of 45 degrees times the cosine of 30 degrees, then a minus sine of 45 degrees, sine of 30 degrees. And then I know what each of those are. Cosine of 45 is the square root of 2 over 2. Cosine of 30 is the square root of 3 over 2. Sine of 45 is the square root of 2 over 2. Sine of 30 is 1/2. And then I always ask myself, is my better factoring or just combining these? So there's two different versions, of how to write this. I could say that this is the square root of 6 over 4 minus, the square root of 2 over 4 would be one way to do it. Or you might notice we can factor a whole bunch of stuff out. So I can factor out a square root of 2. I can factor out the 2 times 2 in the bottom. So another way we might write this is the square root of 2 over 4. And what's left is the square root of 3 minus 1. So sometimes we might see this written one way or the other, but that's an exact answer for the cosine of 75. Now let's think about this in radians for a moment. Let's see, in radians, that would be pi over 4 plus pi over 6. Common denominator there would be 12. So that would be 3 pi and 2 pi. So that would be 5 pi over 12. So we have an exact answer for the cosine of 75 degrees, or we can say that's the cosine of 5 pi over 12. So not only can we find exact answers for things that are related to pi over 3, pi over 4, pi over 2, now we have a way to find exact answers for pi over 12s, which broadens exact answers we can calculate. And the more you play around with this, the more you can find we can extend this to a whole ton of other angles. So part of the homework is applying these sum and difference formulas to get new exact values for angles we didn't know we had before. Okay, now, I did a heck of a lot of work leading to this. I could have made a mistake anywhere. Let's ask the calculator if this is for real or not. So I believe that the cosine of 5 pi over 12, I'm going to stick with my radian version now that I have it, should be the same as, let's see, the second way I wrote it was the square root of 2 over 4 times parentheses, square root of 3, and then minus 1. Cool. Worked. Whew. Didn't make any mistakes yet. At least none I missed. All right, so again, our mission now is to explore these new relationships between sine and cosine and how can they be useful to us. Question.